Here is an example problem you can play with from week 8, class 15. I think it's slide 14. What we have is a space vehicle. You're in a space vehicle here in the green orbit, that orbit. And the space station is also in the orbit. And you are 500 kilometers behind it trying to catch up to it. That's basically the problem, using a minimum fuel approach. This problem also gives us the radius of the Earth. It's 6,371 kilometers. And it tells us that our space vehicle is 500 kilometers above the Earth. That's above the Earth. So we're the same distance above the Earth that we are, by coincidence, behind the space shuttle. And that just happens to be a coincidence. So the first thing we're going to want to do is to find out what our radius is so that we can use the formulas to find our velocity in the green orbit and our period. This for the orbit is going to be equal to the Earth radius, so radius of the Earth, plus our altitude, and that's going to be 6371 plus 500. So 6371 plus 500 is going to give us an altitude of 6871 kilometers. That's going to be our altitude. And now our period is going to be, now that we know that our radius, if we substitute 6871 into our formula for the period, using GM of 4EE to the 14th in the metric system, and the R that we've got at 6871, the period will come out to be about 5668 seconds, 5,668 seconds. You can also calculate the velocity, and if you were to calculate the velocity using the GM over R, then you'll get 7.617 kilometers per second, or 7,617 kilometers per second for your velocity. So to summarize, our velocity is 7,617 meters per second, and the period, the time to go all the way around the circle, is 5,668 seconds from using these two formulas and the R from the radius of the Earth and the altimeter. Okay. Now we want to determine the period of the green orbit and the seconds we're behind. Well, we've got the period, that's 5668. How many seconds are we behind? Well, we're 500 kilometers behind, and we're doing 7,617. So if you divide 500 kilometers by 7,617 kilometers per second, you'll get 66 seconds. So we are 66 seconds behind the International Space Station. So if I make my period of the red orbit 66 seconds less than the period of the green orbit, then after one orbit I will perfectly line up. In other words, the ISS will take 5,668 seconds. If I subtract 66 seconds from that and fly the red orbit in 5,602 seconds, I will exactly line up with the ISS after one revolution of the red. So that's my goal. Now that I know my period of the red orbit, I need to find its apogee and perigee and velocities to complete this problem. So I computed the period of the red orbit. It's going to be 5,602 seconds. And now I have to figure out my velocities, and my delta V's, for delta V1 to get into the red orbit, and then my delta V2 after I've done a red orbit to get back into the green orbit, totally lined up with the International Space Station. So for an elliptical orbit, I'm going to use the elliptical equation, which is going to give me my period of my elliptical orbit. My period of my elliptical orbit is going to be um, 2 pi times the square root of a cubed over gm. And that's going to be very interesting because I know GM, I know my period. So I just have to solve for a cubed, and where 2a is going to be the major axis of the red elliptical orbit from our geometry earlier. So once we know the period of the red elliptical arc, we can solve for a, the half major radius, right? Using that formula for period, from the period, and solve for a, and that's what this solution would look like. You square both sides, and then isolate a, which would be the cube root, the cube root of this expression here, and you know everything. So you could compute your a to be 6,817.8 kilometers. 6,817.8 kilometers. And you also know that the Earth is one of the focal points of the red ellipse. The Earth is one of the focal points. Then if you take 2a minus RA, you'll get the perigee distance. You'll get the perigee distance that's up to the shorter end of the arc. So if you take 2a minus RA, where RA is known, if you take 2a minus RA, you'll get the perigee distance is equal to 6,764 kilometers. That's 6,764 kilometers to the perigee. Now from that RA and that RP, now once you know RA and RP for the red elliptical orbit, you can use the formulas that we developed in class, or that are on my board behind me, for the velocities that depend on RP and RA. Those two formulas will give you the velocity at the apogee and at the perigee. You'd have the two velocities at the apogee and the perigee of the red elliptical orbits. Then once you have those velocities, you simply subtract from the velocity from the green orbit, and that would give you your delta V that you needed to apply. Delta V1 to get into the red elliptical orbit, and then delta V2 to reemerge and get back into the green orbit after you rendezvous with the ISS. All right, hope that helps. Good luck.